Hi, my name is Chinmaya Kelkar. I'm a graduate student in the Computer Science Department at University of Florida. Today, I'll be presenting my final course project in pattern recognition. My project topic is restaurant image classification using convolutional neural networks. Now, let's see what the problem statement is. In the age of millennials who are constantly looking for rich product experiences, image classification is one of the challenging problems in front of the deep learning community. The problem statement that I have addressed in this project is Yelp restaurant photo classification data challenge at kaggle.com. Yelp has millions of users, and a lot of these users upload images of restaurants and submit reviews. These photos have the potential to provide rich information about businesses, in this case, such as restaurants. However, a lot of these images are unlabeled and have to be manually labeled. The project develops a model that generates multiple labels for each image. Yelp researchers have found that users use these labels for several purposes other than just finding restaurants, such as checking if the place has parking or has suitable ambience. Taking this feedback from its customers, Yelp has provided users to search restaurants using tags such as good for lunch, good for dinner, takes reservations, etc. Most of the classification problems involve two main steps, namely training and testing. The label data is split into two parts, training and validation. The model is built using the training data and is fine-tuned with the validation data. The model is then used to predict results on the testing data. The model generates distinct classes for each image which are not correlated to each other. Now let's take a look at what the labels are. At Yelp, users upload images along with submitting reviews about places such as restaurants. For this project, data was provided by Yelp as part of the Kaggle competition. The model developed as part of the project predicts one or more business attributes or labels. The competition by Yelp has predefined 9 business attributes, and they are as follows. As you can see, the labels are good for lunch, good for dinner, takes reservations, outdoor seating, restaurant is expensive, has alcohol, has table service, ambience is classy, and good for kids. The images in training dataset are labeled by Yelp community. Each business has one or more photos. This makes this a multi-instance, multi-label problem. As you can imagine, labeling images is a pretty arduous task. As part of the project, we would like to develop a model that automates this task for us. Before getting into the approach that I have adopted to develop this model, let's understand what convolution neural networks are. A neural network does not take into consideration the spatial structure of the image, so all pixels, whether near to each other or far away, are treated the same way by the neural network. Convolution neural networks can help exactly in this aspect when it comes to classification of images. In a regular neural network, every neuron in a hidden layer is connected to all neurons in its previous layer. For larger images, the full connectivity of the neural network is wasteful and it quickly leads to overfitting of the network. CNN takes advantage of this limitation of neural networks and connects neurons to only a small region in the previous layer. This is known as local connectivity. This aspect is very important when it comes to classification of images. The spatial extent of a neuron is known as its receptive field. So the convolution layer comprises of several learnable filters. As a neuron is connected to a small region in the previous layer, the filters have small height and width but extend through the entire depth of the previous volume. So the approach adopted for this project mainly consists of 4 phases or stages. Phase 1 is the pre-processing where we get the data ready to be fed to the model. Phase 2 is photo level feature extraction. Phase 3 is business level feature extraction, and the last phase is multi-label classification and prediction. In solving complex complex problems, it is always advantageous to use pre-trained CNN rather than developing something from scratch. In this project, I've used MXNet, which has been trained on the ImageNet database. The use of pre-trained CNN is in fact known as transfer learning. I've used weights of pre-trained MXNet model to produce better results. So in stage 1, I've used MXNet to extract photo level features from training and testing data. In stage 2, we'll be extracting business level features from photo level features. And stage 3, we'll be predicting labels for the images using the classification model developed using XGBoost and classifier chains. In the following slides, we'll see what XGBoost and classifier chains are. The dataset required for this project were provided by Yelp as part of the Kaggle competition. The dataset provided consists of the following files. The first file, trainphotos.tgz, contains the training images, and the size of the file is 6.54 GB. The second file contains images for testing purposes, and the size of the file is 6.61 GB. The third file, trainphoto2bizids.csv, is an Excel file which contains the mapping between the photo IDs of training images and their business IDs. The next file is testphoto2bizids.csv, is another Excel file which contains the mapping between photo IDs of test images and their business IDs. The file train.csv contains the labels for the training images. And the last file, samplesubmission.csv, contains the sample format for submission for this competition. Now let's take a look at what MXNet is. MXNet is a machine learning framework that supports multiple languages such as R, Scala, Python, C++, etc., and is developed specifically for deep learning. It embeds declarative expressions along with tensor computation. MXNet is computationally efficient, takes far less memory in comparison to other CNNs. Also, MXNet can be run on any device that has a processor ranging from a small mobile device to multiple GPUs. MXNet is an open source framework. Like Caffe, it abstracts the underlying architecture of a CNN and allows users to define, train, and use deep neural networks. It is used by companies such as Amazon.com for its machine learning related services. For this project, I have used MXNet as deep learning framework. ImageNet is a database that contains nearly 1.2 million training images and almost 150,000 test images and 50,000 validation images. The dataset is organized per world net hierarchy. The large-scale image database has proven useful for several applications. In this project, I have used the pre-trained model to improve accuracy. So the MXNet model has been trained on ImageNet database. So the pre-processing phase contains making the data ready for it to be fed to the MXNet model. So in step 1, we generate the data list file for trainphoto2bizids.csv file and testphoto2bizids.csv file. These files contain mapping between image IDs of the training and testing photos to business IDs. The step 2 involves using the IM2Rec tool, which comes along with MXNet installation, to resize and square crop all images in the training and testing folder to the resolution of 224 by 224. This is the size of the input image that will be fed to the MXNet model. And we store the modified images in record files, namely train.rec and test.rec. Okay, so now using the IM2Rec tool, we'll be resizing the images in the training dataset and square cropping them. So as you can see, I have given the path of the IM2Rec tool, the data list file, the folder that contains the training images, and the results will be stored in the record file. We resizing the images to 224, and as you can see, the images are now getting processed. We'll pause this video and we'll come back when we are done with processing all the images. So as you can see, all the images have been processed. It has taken in all 772 seconds to process all the images. Okay, so now we'll be resizing all the images present in the testing dataset we have given the appropriate path and will be resizing the images to 224 and square cropping the images. So as you can see, the images are now getting processed, and we'll pause the video and come back to it later when we are done processing it. So as you can see, we have processed all the images, and it has taken in all 773 seconds to process all the images. Now let's move on to the next phase, which is the photo level feature extraction. The record files which were generated in the previous pre-processing stage form the input for this particular stage. So the MXNet model Inception 21K, which has been pre-trained on the ImageNet dataset for up to 9 rounds, is first loaded using the function mx.model.feedforward.load. Using the mx.io.image.record.iter function, a data iterator is created using the record file. The batch size is set to 100, and the training dataset has in all 234,900 images. Using the model.predict function, we generate feature vector for each image, and the predictions are stored in a CSV file for the training dataset. The same process is repeated for the testing dataset. The CSV files have 2000 rows for extracted features and 1 row for each image in the dataset. This phase of photo level feature extraction has in all 2349 iterations for the training dataset. Each image in the training and testing dataset have their corresponding feature vector in the CSV files. As said earlier, for this stage, I've used the record files which were generated in the previous phase, which was the pre-processing phase. Now let's see the code that we'll be using to calculate feature vector for the images in the training and the testing dataset. So first we'll import all the required libraries. As you can see, we have imported MXNet, NumPy, Pandas, OS, Time, etc. We have set the batch size to 100, and the total number of batches for training dataset is 2349. The output file is named as featurestraining.csv. We'll be storing the results in a CSV file. These variables will have different values for the testing dataset. The pre-trained MXNet model is present in the directory Inception 21K, and the model has been pre-trained for 9 rounds. Using the mx.model.feedforward.load function, we'll first load the model, and using mx.io.image.record.iter function, we'll create a data iterator through all the images in the training and testing dataset. So we'll be using the record file which was generated during the pre-processing phase. The dimension of the images used as input to CNN are 224 by 224 by 3. The mean RGB values used are 117, and we'll conduct the pre-processing on 6 threads. Now this is a for loop which calculates the feature vectors for images in the training and the testing dataset. So the first column will contain the photo ID of the image, and we'll be storing feature vectors for each image in a CSV file. We print the time elapsed after every 100 iterations, and at the end we print the total time that is taken for us to calculate the feature vector for all the images in the training and the testing dataset. Using the pre-trained MXNet model, we'll be extracting features for each image in the training dataset and storing the results to a CSV file. So in all there are 2349 batches, and each batch is 100 size. We'll pause the video and come back later when it's done processing. So as you can see, we are now done processing, and the total time taken is 138250 seconds. In all, 2349 batches were processed, and the results were stored to a CSV file. Using the pre-trained MXNet model, we'll be extracting feature vector for all images in the testing dataset. So as you can see, we have started the processing. In all, there are 2372 batches, and each batch is a size of 100, and we'll pause this video and come back to it later once we are done processing. So as you can see, we have done processing, and in all there are 2372 batches we processed, and it has taken in all 144849 seconds to complete processing, and the results were stored to a CSV file. From the two CSV files, we have a mapping between photo ID and feature vector, as we have generated a feature vector for each image in the photo level feature extraction phase. However, every business has one or more images. The files train photo to bizids.csv and test photo to bizids.csv have the mapping between photo ID and business ID for training and testing images respectively. The relationship between photo ID and business ID is 1 to 1. By using the two CSV files that contain feature vectors for training and testing images and the two CSV files provided here by Yelp, we can establish a relationship between feature vector and business ID. To capture all information about a business, I've performed certain operation on feature vector. For instance, if a business has two images and the first image shows kids, toys, and the second image shows wine glasses, then labels generated should depict all information about the business. In this example, the labels generated can be has alcohol and good for kids. For every business ID, I've calculated the 60th, 80th, 90th, 95th, and the 100th percentile mean and standard deviation of the feature vector. Also, we ignore all those features which have standard deviation lower than 0.007. These calculations help us capturing rich information about the business. The percentile calculation, mean and standard deviation for each business are stored in a matrix for both training and testing datasets respectively. Now let's move on to the next phase, which is multi-label classification and prediction. We'll be using XGBoost library. Let's see what XGBoost library does. XGBoost library is designed for boosting tree algorithms. Gradient boosting tree algorithm was initially introduced by Friedman. Gradient boosting is an ensemble method where models are added step by step to correct errors of the previous model. It uses gradient descent algorithm while reducing the loss before adding new models. The new models are added until there is no further improvement in the efficiency. Due to the use of multi-threads and regularization, XGBoost is highly efficient and produces highly accurate predictions. It has support for regression, classification, as well as custom objective function. It also allows user to perform cross-validation. The library currently has interfaces in C++, R, Scala, Python, Java, etc. For this project, we'll be using the R interface of the library. Now let's understand why exactly we are using XGBoost. So XGBoost provides regularization that helps reduce overfitting as compared to other gradient boosting machine implementations. It provides parallel processing and allows fast processing using all cores of the processor. XGBoost allows regression classification as well as custom objective functions. XGBoost can handle missing values. A gradient boosting machine keeps splitting the node until it sees a negative loss. Unlike a gradient boosting machine, XGBoost keeps splitting until the tree reaches max depth. And then the tree is pruned starting from the leaves until it keeps encountering a positive gain. XGBoost also allows the user to perform cross-validation. These are the main reasons why I have decided to use XGBoost for this project. Also, along with XGBoost, I have used classify chains. Now let's understand what classify chains are. Classify chains is a binary relevance method that considers each label as a separate binary problem. It is used mainly for multi-label classification. Binary relevance is a problem transformation method in multi-label classification. It transforms dataset into L datasets if there are L labels and learns L binary classifiers. The classifiers learned are then linked together in the feature space. In order to improve the model using XGBoost, we need to perform parameter tuning. Parameter tuning requires a good knowledge of two things: the set of parameters to be used and their values. XGBoost provides linear and tree boosters. For this project, I have used tree boosters. The following parameters were defined for the tree booster. ETA. It is similar to learning rate in gradient boosting machine. Typical values lie in the range of 0.01 to zero point 0.2. I have used value 0.01 for this parameter. The next is max depth. It indicates the maximum depth of the tree. The default value for this parameter, if not specified, is 6. This parameter helps in reducing overfitting, as we are not interested in learning features specific to a certain sample image. I've used the value 10 for this parameter. Subsample. The value of this parameter indicates the fraction of values that are to be randomly sampled for each generated tree. The default value for this parameter, if not specified, is 1. Typical values lie in the range of 0.5 to 1. Very low values can cause underfitting. I have used the value 0.5 for this parameter. The next is call sample by tree. The value of this parameter indicates the fraction of columns that are to be randomly sampled for each tree. The default value for this parameter, if not specified, is 1. I have used the value 0.3 for this parameter. The next is eval metric. This parameter specifies the metric to be used for validating data. We have used the value logless for this parameter. The next is objective. The parameter specifies the loss function that will be minimized in the boosting process. I have used the binary logistic function. It returns the predicted probability for binary classification. The model is then trained on 500 rounds. The trained model is then used to make predictions for the testing data. The matrix used to store business ID and the corresponding feature vector are then fed to the 9 binary classifiers that were trained using the training data. The XGBoost model returns probabilities. If the probability was found to be less than 0.4, the corresponding label was discarded, and if it was found to be greater than 0.4, it was annotated to the final result. The results were written to a CSV file in the format specified for the competition. The output from this stage is a 9-dimensional vector for each business. For example, if the restaurant is good for dinner, takes reservation, has alcohol, and the ambience is classy, then the output vector would be 0, 1, 1, 0, 1, 0, 0, 1, 0. Now in the classification and prediction phase of our project, let's execute the R code. So let's first load all the required libraries. Next, we'll train the 9 binary classifiers, as you can see here, using the labels that are provided in the training dataset and the XGBoost library. Once we are done training the 9 binary classifiers, we'll use them to predict labels for our testing dataset, and we'll store results to a matrix. The labels that have probability less than 0.4 will be dropped, and we'll store the results to a CSV file. Okay, so now let's have a look what the CSV file contains. So the CSV file contains business ID and labels, as you can see here. In all, 10,000 business ID were processed, and the first column contains all the business ID and the second column contains labels, as you can see here. Now let's see how we can evaluate the developed model. In machine learning, a model is evaluated on the basis of 3 factors, namely precision, accuracy, and recall. Precision is the ratio of true positives to all predicted positives. It indicates the efficiency of the model. On the other hand, recall is the ratio of true positives to all true positives. It indicates how many images have been accurately classified. Low precision for an attribute indicates poor filtering for the specific attribute by the model. Therefore, precision is the indicative of efficiency of the model. On the other hand, recall shows the number of images written by the model for a specific attribute. For this particular competition, submission was graded based on F1 score. F1 score is the harmonic mean of precision and recall. F1 score mathematically is defined as 2 into precision into recall upon precision plus recall. The F1 score for the model developed in this project was found to be 0.82. The sample outputs of the developed model are shown in the following slides. As seen from the images, there are some misclassification as the model is not perfect. This shows images of restaurants that are good for lunch. This particular slide shows images that are good for dinner. And this particular slide shows images that are good that take reservations. I would like to take this opportunity to thank Dr. Dapengu for his guidance and help throughout the course of the project. Thank you.